Good afternoon, students. Let us start the class. In the previous class, we were discussing this circuit's functionality, how this particular circuit is going to generate the code vectors. But in the discussion, I made an error at that time. Actually, this R2's output is connected to this XOR gate and there is a feedback here. In a hurry, I did not discuss about this feedback and I kept on computing one after the other. So just to correct that mistake or error, let us do it once again quickly. The input given is 0, 1, 0, 1. So let us do it quickly. It is first is, let me change the color. It is 0, 1, 0, 1. And this 0 is going to go like this, 1 is going to go like this, 0 is going to go like this, 1 is going to go like this for the first 4 clock cycles. At that time now enable is 1. So when the first 0 is here, now already this was having 0 as the output, 0, this was 0 because all are reset. So 0, 0 is 0 here, output is 0 and this 0 is going to come here. So as the very first clock cycle, we will have output, I will write it as, all this R0, R1, R2, they are going to contain 0, 0, 0 only after the first clock cycle. Right, next this 1 is coming. When this 1 is coming, in that next clock cycle, this 0 is coming here, that 1 is coming here, 1, 1 is 1 here, that 1 is coming here now. So the previous 0, this 0 is going to come here. Now there is 1 here. So 1 XOR 0 is 1. Okay. Now R1's input is 1 and this 0 is the input here and then, so R1's input is 1. R1's output is right now 0 in the previous cycle and here it is 0. This 0 is coming here. Next one more 0 is coming. So you can see this is going to be shifted this way because this is 0 coming here. This 0 is going to come here and later on this 1 is going to come here and that 1 is going to become, the last 1 is going to come here. So this one and this one will have XOR. So then it will be 0 here. Accordingly, we will have changes in the output patterns. In the previous session, I went in a little bit hurry and I did not consider this input here. I was simply thinking about only the output going to the position 2 of this switch. So this has to be considered because without this XOR gate at the output, it is not going to create any accurate check bits. So in this way, there is a feedback in this circuit and because of the feedback in this circuit, now I am going to show you the correct outputs. So the first example, it is 0, 1, 0, 1 and you can see, let me slightly zoom out. Now when the input is 0, 1, 0, 1, first it is reset, all 3 registers are containing 0, 0, 0. Next in the first clock cycle, 1 is going to come, the channel output is 1, then 0, then 1, then 0. Again, am I confused? D is 0, 1, 0, 1, MSB coming or LSB coming? I have written as a D3, D2, D1, D0. This is D3 due to D1, D0 only. So first 0 only should come, right? No, I have written the table correctly. In the notes, I have written it different. It must be D0, D1, D2, D3. Okay, let us consider it as D0, D1, D2, D3. So the first one is LSB here. Yeah, that is what is going to be working out here. So first one is LSB here. for the first clock cycle, this 1 is coming here, then 0 coming, then 1 coming, then 0 coming. So accordingly, when the first 1 is coming there, we will have 1 1 0 and the channel output is there 1. Similarly, for the next clock cycle we have 0 1 1 because of all the modulo 2 operations. Then we have 0 0 1, lastly we have 1 1 0. Now later on, enable is going to be 0. When enable becomes 0, whatever is stored in the register, that is only coming out. The other bits are not going to be considered, they are don't care, because ultimately we want only 7 bits. So the other bits, even if they are there, they don't care in the 5th, 6th and 7th clock cycles. That is why I have written X here. So we will have this, we can see here it is 0 1 0 1, you can see here it must be LSB first. So I have done it wrongly here. This must be D0, D1, D2, D3. It must be like that. Now, this is not all right. This must be first D0, then D1, then D2, then D3. This way only the bits are input. So that way only LSB is going first. So that way, even though combination given is 0 1 0 1, it is first 1 coming here. It is now 1 0 1 0. Again, I am sorry for the confusions. It is me only who is getting more and more confused here. Anyhow, I am correcting it now. It is 1 0 1 0. Naturally, at the output 0 1 0 1 is coming as such. LSB is going first there. So you can see accordingly this LSB is going first. This was here, then this was here, then this was here, then this was here. That was 0 1 0 1 as the input. So that itself is going here now. And later on you can see the last 3 bits 1 1 0. That 1 1 0 has come here. Now that 1 1 0 is the check bits that are going along with the data, as this is a 7,4 example. So we can see that in the hardware which we have seen, check bits are generated by means of that particular logic. Let us see the second one. There is a note here, the present input for a flip-flop is the previous output of the previous flip-flop. That is evident here. In any clock cycle, the present input, let us say the present input for this R2 was the previous output of R1, because in that particular clock cycle, only when the clock has made a transition, that is when the output is available. So the previous output of R1 or the previous content of R1 is going to be present input to R2. That must be borne in mind. Anyhow, that is evident. Let us see the next example, that is 1010. When input is 1010, then LSB should come first. So that way it is coming. This is that 0 coming. Then this 1 is coming. That way next is that 0 coming, next is 1 coming. So when this first 0 is coming, initially it was all 0 0 0. Then we have again 0 0 0. Then that 1 is coming as the input now. So we will have the contents of R0, R1, R2 as 110. Please look at this picture back. We can have, as G1 is shorted here, as the input was 0, 0 XOR 1 is 1 only, that 1 itself is coming here. So whenever we have 1 here, then naturally here we have 1. Here if it was 0, then here the output is 1. So naturally R1's content is 1 now. Okay. So this way we will proceed for the next example. Next set is 110. In the third clock cycle it is 011. The fourth clock cycle proceed in the same manner, it is 001. Afterwards anyhow other inputs are don't care. So I suggest you to manually work out all these things by taking that particular picture in front of you. Otherwise, I am only showing my tabulations. You have to personally work it out so as to have no errors in the computation of these bits in the contents of registers. Ultimately, you have to get this 1010 as the output, and we are getting 001 as the check bit stream. If you have to get this correct check bit stream, you have to actually work it out using the circuit diagram given above. Okay. So this way, gradually let us move on to the third example where input is 1001. So now LSB MSB confusion is not there because LSB and MSB both are same. Anyhow, LSB only should come first. LSB only should come first. LSB itself is coming here first. Next, this bit is coming here. This way only it should happen. So finally we get 1001 going out in the channel, and then 011 is following, that is the check bits corresponding to this particular data stream. So this way we have seen how in the transmitter encoding is happening using a simpler hardware. That was because of the usage of generator polynomial. We used polynomial only, even though later on we may use matrix also for the sake of simplification, but in this particular hardware we did not use the matrix at all. We used only the polynomial, and the polynomial is implemented using XOR gates and the registers. In a similar way, let us see now how at the receiver syndrome calculation circuit is going to work with the same logic. All the code vector polynomials are now divisible by g of x. This we know. Hence, if syndrome is obtained by means of division, and if the syndrome is 0, then the received vector polynomial z of x has no errors. We know syndrome is obtained by means of division. If the syndrome is 0, then the received vector polynomial z of x has no errors. Please remember, here the syndrome calculation is happening by means of polynomial divisions, right? Now, when the syndrome is non-zero, if the vector polynomial z of x is 0, that means it is no error. But when the syndrome is non-zero, how exactly we should compute? When the syndrome is non-zero, then z of x divided by g of x is equal to q of x plus s of x divided by g of x, where s of x is the syndrome, q of x is the quotient, z of x is the resultant, g of x is the generator polynomial. So through this equation, we can have the hardware now. Z of x divided by g of x is equal to q of x quotient plus s of x by g of x, syndrome divided by generator polynomial. Now, syndrome s of x is of degree n minus k minus 1 or lesser. It depends on the polynomial itself. This division can be implemented by means of the following circuit now. It is a similar circuit, only thing is z of x is coming. Z of x means the code vector which has gone through the channel now. Now z of x may be having errors, may not be having errors. We don't know. We will have to find out. So z of x itself is going to be input to the hardware. Hardware is now slightly similar. Only thing is there is an addition of AND gate. Otherwise hardware is slightly similar. And another difference you can see is it is the reverse order. In the reverse order, in the sense, you will see XOR gate in the beginning, you will not see XOR gate at the end. In the generator hardware, you saw XOR gate at the end. There was no XOR gate in the beginning, there was a register. Now this is the reverse order. Procedure is the same. Only thing is, there are now two enable signals. Let us see what for are the two enable signals slightly later. But you can observe this now. This hardware is same as the previous hardware. As you know, G0 is always going to be 1. The term has to be there. Whether term is there or not, we should have such connection. So you can see, but it is coming to an XOR gate now. It was not it is not going to a register where it was going earlier in the generator circuit. So then instead of R naught, here we have written S naught, because what we want is, now we want a syndrome. There we wanted the check bits. Now here we want the syndrome bits. Otherwise the circuit is the same. Let me go on. Now the steps are, initially all the flip-flops are reset, and then gate 1 is turned on and gate 2 is turned off by making enable 1 equals 1 and enable 2 equals 0. Gate 1 is on, gate 2 is off. Enable 1 is initially 1, enable 2 is going to be 0. That is because initially in this hardware we have to compute the syndrome vector for those many clock cycles. After those clock cycles, whatever is going to be stored in these registers or flip-flops, at that time enable 1 is going to be made 0, enable 2 is going to be made 1. So in the next clock cycles, the stored syndrome vector is going to come out at S of x. That is the idea here. In the previous circuit, we had only one single enable, and we made it 0 when we wanted to take out the check bits. But here, first we have to compute the syndrome bits, for which we require enable 1. Later on, we have to take out the stored bits that are in the flip-flops. That is why enable 2 is there. So we can mention that enable 1 is for computation of the syndrome bits, and enable 2 is for taking the syndrome vector out of the registers. That is the idea here. So initially all the flip-flops are reset, and then gate 1 is turned on and gate 2 is turned off by making enable 1 equals 1 and enable 2 equals 0. Now the second step is the received vector z of x is then shifted into the register. Now as it is a serial communication, one by one the received bits are coming into the hardware now, and this process requires n clock pulses. After the entire vector is shifted inside, the contents of the register will be the syndrome vector. Look at this. After the entire vector is shifted inside, the contents of the register will be the syndrome vector. Later on, enable 1 is made 0, enable 2 is made 1, and the stored syndrome vector is taken out of the registers. So now, gate 1 is turned off and gate 2 is turned on by making enable 1 equals 0 and enable 2 equals 1. And the syndrome vector is shifted out of the register in the next n minus k clock pulses, and the total process requires 2n minus k clock pulses, unlike the previous case. In the transmitter's case, we required only n clock pulses. Here, for computing syndrome, we require some clock pulses. Later on, for taking out the syndrome, we require some clock pulses. We require totally 2n minus k clock pulses. Let us see an example now. For a 7,4 cyclic code, the received vector z of x is 1110101 and g of x is 1 plus x cubed. Draw the syndrome calculation circuit and correct the single bit error. Now it is 1110101. Let us see. The syndrome calculation circuit is, now you can see 1110101. Initially we have XOR gate, then we have a register. As the generator polynomial is 1 plus x cubed, you have G0, you have G1. As x square is not there, you don't have one more XOR gate here. And lastly, anyhow, for x cube, there is no need of XOR gate there, which we have discussed earlier. Now, this is the syndrome calculation circuit with 2 AND gates at the output. Initially, enable 1 is made 1. Let us see. Let me see. I should not get confused now at least. Let me see. Now this is 1, this is 0. When this is 1, initially this 1 is coming. And this one and this one output is 0 here. In the very first clock pulse, input is 1, and here Wait, again I am confusing. S2 is 0, right? S1 is 0, right? S0 is also 0. Output of all the three registers is 0. Now when enable 1 is 1, S2 output is 0. So here output is 0. When this is 0, this 0 is coming here. And 0 XOR 1, output here is now 1. Okay, sorry, output of XOR gate is 1. That means the present input of S0 is 1. The same 0 is coming here. 0 XOR 0, this is now 0. And again, this is also 0. That way it goes on. Now, at this particular point, the contents of S0, S1, S2, initially it was 0, 0, 0. Now it is 1, 0, 0. Contents of S0, S1, S2 is 1, 0, 0. Still enable 1 is 1. Here this is again 0. Next 0 is coming. Next when this 0 is coming, output here is now 0. So this 1 is now coming here. 1 XOR 0 is 1. So the next content of S0, S1, S2 will be 0, 1, 0. This way it goes on. Let me show you the answer only. This way it goes on, and let me see whether I am correct. Yeah, at least now I am correct. So for the first 7 clock pulses, enable 1 is 1 and enable 2 is 0. For the next 3 clock pulses, enable 1 is 0, enable 2 is 1, as is evident. For the first 7 clock pulses, you see here, we have to take all these 7 bits inside. So we require 7 clock pulses. Next 3 clock pulses are only to take the syndrome outside. So totally we require 10 clock pulses. That was also mentioned as 2n minus 1 clock pulses, right? Here we have mentioned, 2n minus k clock pulses. So 14 minus 4 clock pulses. So let me show you the result. First is reset 0, 0, 0. Next clock cycle, input is 1. So output of the registers is 1, 0, 0. Next input is 0, 0, 1, 0. And next it is 1, 1, 0, 1. Next it is 0, 1, 0, 0. Like that it goes on. And last 3 are 1, 1, 1. We have this 1, 1, 0, 1, 1, 1, 0, 0, 1. Now the 0, 0, 1 is the syndrome. Now we have a non-zero syndrome. If there was error, we were supposed to have 0, 0, 0. Now there is error here. This is 0, 0, 1. Now the 0, 0, 1 has to be taken out from the registers by making enable 1 equals 0 and enable 2 equals 1. So as S of x is 0, 0, 1, syndrome is 0, 0, 1, it indicates an error. For correcting the error, now there are 2 methods as explained below. There are 2 methods. In the block coding, we were simply checking for the syndrome in the Hamming matrix or the parity check matrix. And we used to find out the row in which the syndrome was present, and that particular position we were correcting the error. Now here, how to correct the error when we have a non-zero syndrome? We have 2 methods now. Let us see. Method 1. When a non-zero syndrome is observed, it indicates an error for which we have to obtain the position at which the error exists. And so after the 7th clock pulse, the gate positions are retained as they are and zeros are fed into the shift register from 8th clock pulse onwards. This is first method. We are assuming that we don't have a parity check matrix now because we are going through polynomial methodology. So when we don't have a parity check matrix, how do we find out the position? For that also there is a solution. After the 7th clock pulse, the gate positions are retained as they are and zeros are fed into the shift register from 8th clock pulse onwards. Now this is continued until the contents read S0, S1, S2 equals 1, 0, 0. From the 8th clock pulse onwards, we further feed zeros. Now, we should get S0, S1, S2 as 1, 0, 0. Now, the number of clock pulses required to obtain this particular syndrome vector is 1, 0, 0. Indicates the position of the error from the right side of Z of x. I am going to show you the procedure here in a pictorial format. You can see. 8th cycle we give input 0. Already it was containing 110. S0 and S1, S2 was containing 110 earlier. Again 9th cycle, 10th cycle, 11th cycle, 12th cycle. We will keep on feeding zeros. 110, 011, 111, 101. We are getting again 100. Okay. Now when we get this 100, we will have to continue until the contents read 100. That is the magical combination there. Now when we get 100, how many clock cycles are over now? 5 clock cycles are over. Now as 5 more pulses were required to obtain the vector 100, the vector error is in the 5th position from the right side. It is the 5th position from the right side. 1, 2, 3, 4, 5. So what was our input? Our input was 1110101. 1, 2, 3, 4, 5. As 5 clock pulses were required for obtaining this 100, now in the 5th position we have this error. So now the vector is corrected. It is 1100101. This is the corrected vector at the receiver. So please remember, syndrome we have obtained 001, and we will continue feeding clock pulses further, and we will continue giving zeros at the input until we get 100. Okay. Then why 100? See here in 001 also, this is S0, S1, S2. This way we will get this 100, and the number of clock pulses indicate the position in that particular vector received. This is the first method. The second method as such is to match it with the Hamming transpose or parity check matrix. This method is to match the syndrome vector with the Hamming transpose matrix. Now Hamming transpose is written here. Okay. And the syndrome vector 001 is present in the 3rd row of H transposed. And the error exists in the 3rd position of Z of x, but it is from the left side. In the earlier method, we corrected it from the right side. Now in this method, we correct it from the left side. It is one and the same. Therefore, the error vector E is 001, 0000. Corrected Z of x is 1110101 modulo to addition with 0010000, that is 1100101. So there are two methods now. First method is again going for the serial fashion, adding zeros, inputting zeros at the input and proceeding further with the number of clock cycles for obtaining another combination of S0, S1, S2. And then based on the number of clock pulses which we feed, we will find out the position of the error there. The second one is, as usual, go for Hamming transpose matrix and find out the row, and when you find out the row, now you correct the position from the left side, not from the right side. Just a minute. Okay, let me continue. Let us have an exercise now. With reference to the previous exercise, correct the received vectors 0 1 1 1 1 1 1 and 0 1 1 1 0 0 0 without using Hamming transpose matrix. We had done that exercise earlier in the same serial fashion. We will have to proceed now with the same example. I am writing the answer here. First, let us take z of x received is 0 1 1 1 1 1 1. So, you can see here it is in this order 0 1 1 1 1 1 1. So, first it is 0 0 0. Next we have 1 0 0. Then because of those XOR gates we have 1 1 0 1 1 1, like that it goes on. Let me stop annotating. Now, after the 7 clock pulses, we have this syndrome now, that is 1 0 0. It is already highlighted here. We have the syndrome now 1 0 0. Now, this indicates an error. When it indicates an error, we have to proceed further by feeding zeros. Now, you see, when you proceed further with all these zeros, we have this 1 0 0, then we keep on proceeding further. We will have to add another 7 clock pulses, totally 14 clock pulses, and we get this syndrome vector again here. That means the error is in the 7th position from the right side, right? Because we are getting the same thing here now. We will have to work out until we get the same syndrome vector. That is the beauty of this circuit. We will have to keep on feeding zeros once again until you get the same syndrome vector. Earlier I showed you that, and I showed you in the flipped fashion only to show you LSB and MSB sides. Otherwise, we have to keep on working until we get the same syndrome vector, that is 1 0 0 in this particular case. For getting this 1 0 0, we had to apply again 7 clock pulses. So, the error is in the 7th position from the right side under error. We have to move from right side. So, the corrected z of x is now 1 1 1 1 1 1 1. Now, this can be verified from H transpose as well, where 1 0 0 is present in the first row. Let me show you H transpose, where it is present in the first row, which means first position from the left side now. You can see it here, 1 0 0 is present here. 1 0 0 is present in the first position. That means from the left side, first position bit is having error, that needs to be corrected. Now let us move on to the second example, 0 1 1 1 0 0 0. So it is written here now 0 0 0 1 1 1 0. Now this is the received vector 0 0 0 1 1 1 0. So LSB first here. So this way, that is what is coming here now 0 0 0 1 1 1 0. Now correspondingly you can see after the 7 bits are input, we have this syndrome, that is 1 0 1. It is shown here. Now when it is 1 0 1, now once we apply one additional clock pulse itself, we are getting this vector 1 0 0. Look at this. We were supposed to get this 1 0 0. That is the magical bit stream, as I had mentioned earlier. Now, as soon as we put this particular 0, next clock pulse, we are getting this 1 0 0, which simply means what? Only with one clock pulse we have got this now. That means the first position itself is having this error, right? So corrected vector has to be 0 1 1 1 0 0 1. So the very first position itself is in error from the right side, and that is being corrected. I write it as 0 here. It is not 0. It is I am just highlighting the position. Don't think that I have written 0 there. No, I am highlighting that first position itself, because by applying only one clock pulse, we got this vector 1 0 0. So we should continue this procedure until we get the syndrome vector 1 0 0. That is the point here. That 100 is the particular magical bit stream, I should say. Now don't confuse this 100 with this 100. No, this is different and this is different. Here we were getting that flip-flops contents as such there. And this is the syndrome. This is the syndrome. But we will have to work out further for obtaining this 100 bit combination. That is the idea here. Hence, the error is in the first position from right side. Therefore, the corrected z of x is 0111001. The obtained s of x 101 is present in the 7th row of H transposed. Obtained s of x 101. You can see here, it is in the 7th position now. It is in the 7th position. That means 7th position from the left side or first position from the right side. So that way, finally it is verified. Now, the question is, what is so special about this 100? That is the question. Can anybody find out from the same diagram and tell me the answer in the next class? In this method, we are inputting zeros further to the same hardware so as to get 100. That 100 is the magical bit stream here. Now the question is, what is so special about this 100? How are we getting this 100 after those clock pulses? Anyhow, generator polynomial and syndrome polynomial, we are using the same type of hardware with the XOR gates and the flip-flops. There it is only a logical computation of the check bits in the first case, and it is a logical computation of the syndrome bits in the second case. But when we continue the procedure further without using H transposed, using method 1, when we continue the procedure further, we have to wait until we get this 100. Now the question is, why this 100 is decided upon? That is the question. What is the relationship of this bit stream 100, which I mentioned as a magical bit stream? Only in the first example, we had it in the reverse order. Okay, that was coincidence there. In that example, it was simply a coincidence where we had 001 and we were searching for 100. That was a coincidence. But the question again, I am repeating, what is so special or magical about 100? Why should we continue the procedure until we get this bit stream 100? So, if possible, try to find out the answer, and in the next class, tell me the answer. I will be happy if someone tells me the answer. With that, we have ended the discussion of the hardware implementation of generator polynomial and the syndrome vector. I am almost coming to the end of this cyclic codes discussion. Okay. We will discuss now one particular special code called expurgated Hamming code. Let us see what is that now. When we have a n minus k systematic cyclic code, n comma k minus 1 code can be easily obtained by making use of the same g of x. That is the specialty again here. Look at this. When we have a n minus k systematic cyclic code, sorry, it is not n minus k. While writing, I have made a mistake here. It is n comma k. When we have n comma k systematic cyclic code, n comma k minus 1 code can be easily obtained by making use of the same g of x. Such code is called as the expurgated code, in which the message bit length is reduced by 1 and the check bit length is increased by 1. We will see an example later on. Now, we can easily get another code by using the same generator polynomial. That is the idea here. So let us say we have a 7,3 cyclic code. We can get a 7,4 code by using the same g of x. Why? Because g of x and h of x both are factors of x power n plus 1. In such a case, g of x becomes h of x in this case, h of x becomes g of x in this case. Is it so? Is it not so? No, we are going for a n comma k minus 1 code. Okay. So g of x will not become h of x will not become g of x. But the point here is, we had that x into g of x squared into g of x cubed into g of x. We had made use of them also earlier. So that way, we can easily compute an additional coding stream by using the same g of x. In such a case, this is called as an expurgated code. Here the message bit length is reduced by 1 and the check bit length is increased by 1. Naturally, because we are going for n comma k minus 1 here, means the check bit has to be increased by 1, because n remains the same, right? N remains the same. Instead of 7,3, we have to go for 7,4. Now we can obtain that 7,4 code by using the same g of x. Then such code is an expurgated code where message bit will be reduced by 1, check bit length will be increased by 1. Okay. So as 1 plus x is a factor of x power n plus 1, the generator polynomial for the expurgated code is now what? g1 of x equals 1 plus x into g of x. Let us see an example now. For the 7,4 systematic cyclic code, the generator polynomial given is 1 plus x square plus x cube. Construct the expurgated 7,3 Hamming code in the systematic format itself. Now given g of x is 1 plus x square plus x cube, g1 of x multiply by 1 plus x. Now g1 of x is 1 plus x into 1 plus x square plus x cube. We get 1 plus x square plus, 1 plus x square plus x power 4. Now this is g1 of x. Now let us find out x into g1 of x and x squared into g1 of x. We obtain these. Now we can write the generator polynomial. We have the generator polynomial. We can write the generator matrix. Generator matrix is of the order of 3 cross 7. Now it has to be formed as P piped with I3. So G1 is now, in accordance with that, these three expressions, 1 plus x square plus x power 4. In accordance with that, we can write here G1 is 1 1 1 0 1 0 0. Then see x square, x cubed, x power 5. You can see here x corresponds to this, x square corresponds to this, x cubed corresponds to this, x power 5 corresponds to this. So we have 0 1 1 1 0 1 0. Then finally x square, x cube, x power 4, x power 6. We have this, we have this, we have this, and lastly we have this. So we have constructed a generator polynomial. Now is it having that identity matrix? 1 0 0 0 1 0 1 0 1 is there. We have to obtain 0 0 1. Now we will have to perform a linear addition operation or row transformation. So we will simply do R1 plus R3. R1 plus R3. 1 plus 1 is 0 and 0 and 1. We will simply do R1 plus R3. When we do R1 plus R3, we are getting this particular generator matrix. Now using the generator matrix, all the code vectors can be obtained. The code vectors are already written here, where the Hamming weight is 4. That means this particular code can detect 3 errors, dmin minus 1. Here there is no dmin, all are same here. It can detect 3 errors and it can correct 2 errors, dmin minus 1 divided by 2, 4 minus 1, 3 divided by 2, 3 by 2, 1 error only then, right? 1 error only. This code can detect 4 minus 1 equals 3 errors and can correct 4 minus 1 by 2. 3 by 2 is 1.5. it can detect only one error because there is no half error. There is increased error detection capability in case of this expurgated code. You can see, we had seen the example of 7,4 code earlier. Now we are seeing a 7,4 code here, which is having a increased detection capability. It can detect 3 errors, but it can correct only one error. So that way, sometimes the expurgated codes will have better abilities when compared to the regular codes. That is the finding here in this particular topic. So with this discussion, I am going to end the class for today. See you in the next class. In the next class, we will be completing the discussion of the cyclic codes and we will gradually move on to the discussion of